All right, in this chapter, we're going to get a basic idea of organic chemistry, or what you would call OChem if you have to take chemistry in college. We're going to look at specifically carbon bonds and how they are structured, and look at the molecular and structural formulas that represent those organic compounds. And then we'll look at something called isomers, the different structures of the same organic compound. So section 1 is going to be really short, and section 2 is quite longer. We'll look at both of those in time here. But organic compounds, we've learned that they contain carbon, but not necessarily all carbon-containing compounds would be classified as organic. For instance, sodium carbonate, Na2CO3, carbon monoxide, carbon dioxide. We do apply those a lot in inorganic chemistry, and so there are some exceptions to the idea that everything organic contains carbon. But organic compounds can be defined as covalently bonded compounds containing carbon, excluding, like I just mentioned above, carbonates and oxides are the two big exclusions there. So I'll highlight those for you to keep those in mind. But everything else with carbon we would really consider to be organic. The structure and bonding that carbon allows, because it is able to form these long chains, carbon has those 4 valence electrons that would like to attach to other carbons that in addition bring 4 more valence of single bonds, double bonds, triple bonds. We can have all sorts of combinations of all those, and this allows us to make these complicated chains of carbon atoms. So this idea of catenation is the addition of adding more and more chains or rings to form these structures. Hydrocarbons have only carbon and hydrogen. They're kind of the main things we're going to look at in the next section. Other organic compounds contain hydrocarbon backbones to which other elements like oxygen, nitrogen, sulfur, and the halogens can be attached. And we'll talk about those a little bit as well. Compounds that have the same molecular structure, but they have, same molecular formula, but different structures, they're called isomers. So this idea, C2H4O, that's a molecular formula. It can represent either ethanol or dimethyl ether, depending on how it's structured. So I think I have that on the next slide here. Dimethyl ether is like on the left, where we have carbons with an oxygen sort of sandwich in the middle, hydrogens all around the carbons. But if we were building these with molecule sets, we could also put the 2 carbons together, throw an OH on the end of one carbon, and fill in the rest with hydrogens, and we would have ethanol. But notice both are C2H4O technically. We have a structural formula for an isomer of C4H10 shown here. I drew it one way with the 4 carbons all in a straight line with hydrogens all around surrounding it. You could also have like a more of a T shape where the carbons form a T, and then you just surround all the extra remaining spots with hydrogens around each of the carbons. Sometimes we actually condense structural formulas to make them easier to read. We can really get basic on these formulas. But if I just write carbon, it's understood that, an outside carbon like this would have 3 hydrogens branched off of it. This middle carbon, it already is attached to 3 carbons, so it's just going to have 1 extra H. And same with these outside carbons, they're going to have 3 H's around it. Instead of drawing this huge, gigantic structure, we can simplify it a little bit. We can actually simplify it more than that, as we'll learn. If I want to show you this idea of a skeleton structure now. We'll look at it in more detail on the worksheet, but if I have any time I have a end of a line, that represents a carbon, or if I bend the line, it's a carbon. So 1, 2, 3 carbons could be represented by these 3 points on here. And this whole structure, believe it or not, if I just add one more carbon down here, this represents this. Because what I assume is each of these ending points represents a carbon, and then off of each carbon will be enough hydrogens to fill out that structure. So that's assumed in my skeleton structure that each carbon has 4 links to it. But again, this whole structure can just be represented by, and I can write it in different orientations. I could write it like that. As long as I have those 4 carbons represented, that's what this structure tells me. But those structural formulas don't accurately show the 3D shape. We know this from when we represented molecules last year. But the ball and stick model gives us a little bit better idea of how it's oriented in 3D space. We can kind of turn it around, face it in different directions. A space filling model does a little bit better, showing us, reminding us that, these aren't solid objects. There's orbitals, and there's kind of fuzzy boundaries around each of the atoms. I think we already talked about this, the idea of structural isomers with C4H10. And I had them all drawn in a straight line versus in the T shape. We already kind of looked at that. By the way, just to show you the skeleton form of butane, you'd have 1, 2, 3, 4 carbons. And then again, that's all I have to draw. That means butane, because off of every point, we're assuming there's enough hydrogens to complete it. Geometric isomers, these are ones where the order of the atom bonding is the same, but the arrangement is different. So with it's called 1,2-dichloroethane, and we're going to learn how to name them that way next section. But notice how these are the same structure even. You got the double bond between the 2 carbons. The only issue is, or the only change is I switched these 2 around, and now hydrogen is on the same level as one chlorine, and the other hydrogen is on the same level as the other one. Notice the structure is the same, but it's the geometry that has changed. And again, just another type of isomer where you have the same formula, same structure, but different geometries. So that's it for section 1. I'm going to pause here, and we're going to go on to section 2, learning how to draw the structure in naming hydrocarbons.